My name is Peyton Holston. This is my submission for Lab 2 for Physics 2211. So in this lab, we're essentially exploring Newton's second law as it relates to motion with a non-zero net force. And these forces that we're exploring is essentially the force of gravity and the drag force. The force of gravity being the force that pulls objects toward the surface of the Earth, and the drag force is the force that opposes that motion, which in our case is air resistance. We'll also explore terminal velocity, which is the maximum velocity of an object as it falls through a fluid. So it's when the velocity is constant as an object is falling. So in my experiment, I dropped a pair of socks from a height and tracked its motion using Tracker. And in doing so, I was able to get the position over time as the sock fell to the ground. I then modeled that data using VPython and then charted the data I received in the chart you see here. Now, in this particular model or computer model, I did not include the drag force, so I could see just what the force would look like in the absence of air resistance. And as you can see, the model was somewhat close. The observed data is in the blue and the model data is in the orange. So actually, which against what I hypothesized, my model actually underpredicted the distance that the socks fell, which could be due to a number of reasons. I could have miscalculated my tracker data, or I could have messed up on the model somewhere. But as you can see here, with the drag force, my model data was even less accurate as it was even higher above. And for my B, I just, since the actual drag force would have made it less accurate, I just put in a very small drag force just to see what would happen if drag force was included and how the model would change. So that's why it's even less accurate. But I was aware when I made the change that the model was going to be like that. I just wanted to include a small drag force to see how the model would change. Here you can see all three data points, and you can see, of course, as I was saying earlier, that the model data with drag included is higher up, which is expected because the drag force would slow down the motion of the object, therefore slowing down the time it takes for it to reach a certain distance. Here you can see the code that I used to create my model. I measured on a scale the mass of this pair of socks, which came out to 27 grams, which would be 0.027 kilograms. I took the initial position and initial velocity from the tracker, and then as you can see, there's the time initialized and the delta t initialized, the force of gravity, which is 9.8 meters per second, and the unit vector for the positive y-axis. And in this case, my B was 0 since this was for the absence of drag force. But when I included drag force, I set B to 0.01. This is the calculation loop without including drag force. So as you can see, the force of gravity, which is denoted by force underscore gravity, is the mass of the ball times gravity times the unit vector in the y direction. And so the total net force would be equal to the force of gravity. And then I just use the velocity and position update equations to calculate the velocity and position over time. In this particular calculation loop, I included the drag force, which takes in the proportionality constant B times the magnitude of the velocity squared times the vector in the y direction. And then our net force will be equal to the force of gravity plus the drag force, which would be acting in opposite directions. And then I use the velocity and position update equations to calculate the velocity and position over time. Now, some further questions that were posed was which model predicted a terminal velocity? And from what I found, neither model truly predicted a terminal velocity because the velocity was never constant over time in either of the models. And that could be because of the weight of the object that I used was so light that it never had a chance, and the distance that I dropped it from was so short that I just never had a chance to reach terminal velocity. And in the case of would the terminal velocity be affected by throwing the object, that answer is no, because the terminal velocity is intrinsic to the system and the fluid being traveled through. So me adding a force to it initially would not be able to change the terminal velocity. In actuality, the computer model, which only accounted for gravity, should have had a much steeper slope of change in position than my observed data, because in my observed data, the drag force should have been apparent. So that must mean there may be some error in my calculation or in the way that I tracked the motion of the object in Tracker. But overall, I was still able to explore the physics concepts that were presented forth in class.